Hi everyone, I'm Yuxiao Yang, and I am an assistant professor in the Department of Electrical and Computer Engineering in CECS, and I joined UCF in August 2020. And in this project, I'm collaborating with Dr. Stephen Berman, a professor of neurology in the Department of Internal Medicine from COM, and we are trying to develop and validate an intelligent neuron control system for treating neuropsychiatric and neurological disorders. And I would like to thank both CSCS and COM for funding us so that we have this very nice opportunity to investigate this topic. A bit more about our team. So my expertise is in developing closed loop brain machine interfaces for estimating as well as controlling different type of brain states, for example, related to mental disorders as well as movement and cognitive functions. So the tools that I use are basically systems and control theory, machine learning, as well as knowledge from neuroscience. And my collaborator, Dr. Berman, his research focuses on using molecular biology, biophysical modeling, as well as clinical trials of new medicines to probe the neural systems to find new and better treatments for neurological disorders. And in this particular project, we are going to develop a new intelligent system that uses deep brain stimulation to treat neuropsychiatric and neurological disorders. So I will hand over to Dr. Berman to give an introduction of the brain disorders.
Okay, thank you very much for the introduction, and I'd like to thank both the computer science and internal medicine department for the sponsoring and funding the award. And I'm really honored to be here. The picture you see in front of you depicts 4 very important diseases that we're interested in, and I've been interested in these for a long time. Time does not permit detailing these, and I think most people, simply from the names, have some idea of what they're all about. And those have been, of course, worked on for many, many years, really for centuries. But it's only been there's only been rapid progress on any of these since, and I'll give you a little historical background, since the mid 1800s, the end of the 1800s. And much of this started with a researcher named Ramon Cajal, who used all the scientific tools available of his day to figure out how to image for microscopy neurons so that he knew what was going on in the brain and other parts of the nervous system, to which he showed that it wasn't just a pile of mush like it looks like if you look at the brain in your hands and cut it grossly. But he was able to make these beautiful anatomical drawings. What you see depicted is a slide from the retina, and he did tens of thousands of these himself with his own hand, looking at the complex networks. And, you know, I saw these back, you leave the picture on of Faraday. And I saw these when I was in college. I was really interested in things like that because I was both heading toward medicine as an ultimate career, but I was also in something which they called at University of Illinois engineering physics. And when I looked at these diagrams, I said, hey, that in a way that reminds me of a circuit diagram. You've got different components. They're connected together. It looks like some kind of network, like they're processing information. Of course, that was a long time ago. And even then, it was before the time where you could actually intervene in that way and actually try to inject some kind of electrical stimulation into them, though certainly things were beginning to be talked about, and you certainly could record from the brain and other parts of the nervous system in that time. And it's also interesting that Ramon Cajal himself felt that electrical signals were going through these networks. And it's not surprising I put the picture of Faraday up there, because Faraday had also brought the science of electricity along very, very far before the time of Ramon Cajal. So those things have been poised to get together for a long time. So I'll just focus mostly now on Parkinson's disease. It's the easiest one to see what it's all about because you can actually see the symptoms with your own eyes, which I'll show you in a moment.
Anything feels uncomfortable, let me know.
In fact, here it is, a Parkinson patient with a bad tremor. He's hooked up and his doctor is adjusting the stimulator.
Feel that?
Yeah.
You can see he reacted to it and the tremor is slowing down.
As I increase the voltage, you sometimes get a little buzz as the voltage increases. And I can tell we haven't stopped anything with the tremor yet. Do it a little bit slower.
There it's pretty much stopped.
I should go back and forth to my finger. Back
It's
to
a
your nose.
very stable coordination now. Moves very well.
Now rest your both.
Okay. And so what you saw was the result of having a stimulator that it's controlled externally, and then a wire goes in and down into the brain with a deep probe that can stimulate at multiple levels at certain points in the brain that has been worked out both theoretically and by trial and error. And you just saw the doctor adjusting it. And I think it's very dramatic the way it stopped the tremor. Now, as he goes through the day, he'll be under either greater or lesser tension. He might be understimulated, overstimulated. Parts of his symptoms will come back when he goes to sleep. He doesn't even need it that much, but usually people leave it on which wastes the battery, because if they get up in the middle of the night, they may be shaking too badly to turn it on. So the big problem with that, though it does work for suppressing symptoms quite a bit, one big problem is that it doesn't last, it doesn't maintain, and therefore what you really would want, since you can't be hooked to your doctor all the time, is you'd like your stimulator itself to have some intelligence built into it. And the usual way it's very hard to do that with the sort of open loop concept. And Dr. Yang will talk more about the details of that. You really need something called closed loop stimulation, which we have in the next slide, which again, the specific details that can track what's going on, whether it's linear or nonlinear, can track it in time. And you want something that will handle noise, which current things available cannot do, as well as things that are at least somewhat generalizable, so that you could have one approach which could be readily modified so that you could do multiple diseases. And the main goal on this is to really give people like intelligent control so that kind of stimulation and suppression of their symptoms can last throughout the day. As far as I'm now going to, so I think the main thing to keep in mind is just that video of how well that worked for that man and how great it would be if you could have that continue to work throughout the whole day, asleep and awake, and not need to, be brought in for adjustment, but could very readily adjust itself and regulate itself. And I think I will now turn it back to Dr. Yang, who will detail what our approach is in trying to improve the situation for stimulation like that.
Sure. Thanks, Dr. Berman, for the introduction. So as we briefly mentioned, in this project, we are trying to build a closed-loop intelligent system that can automatically observe neuron activity in real time and then figure out what is the best type or what is the best intensity of deep brain stimulation we should use to stimulate the brain so that we can control the symptom to be at the target level. So in this project, we have two main goals. First of all, we want to, of course, in theory and in a computational model, develop an intelligent neuron control system that is model-based, adaptive, and robust. And also, we wish the system to be generalizable across different types of disorders. And the end goal is to be able to have a system that can enable personalized DBS treatment for each individual patient. And at the same time, once we build the algorithms, we also want to validate the system, of course, within the scope of this project, with different types of neurophysiological models. For example, models that describe Parkinson's disease, depression, and epilepsy. So we will take these models at our simulated brain and to simulate the brain at microscopic, mesoscopic, as well as macroscopic levels so that we can test our algorithm. So more specifically, we have 4 aims. First one, we want to build a dynamic model to describe the dynamics of the network activity, as well as the effect of stimulation on activity. The main contribution in our approach is that we also explicitly model a general class of nonlinear model uncertainties to take into account all these unpredictable situations that can happen in reality. And of course, we will pick our model to be this form so that it's easy to design robust and adaptive controllers. And next, based on this model, we are going to develop a robust and adaptive controller that can adaptively estimate these uncertainties in real time and also have the ability to robustly handle noises. And with this algorithm, we also want to theoretically establish the stability of the algorithm using the Lyapunov theory, as well as the L1 adaptive control theory. And after that, we will do numerical simulations to validate the models. And essentially, we will do 2 sets of simulations. The first set is to just simulate general nonlinearities within this particular model and to investigate the performance of the algorithm. And the other set of simulation is to use neurophysiological models for Parkinson's disease, depression, as well as epilepsy to show that the algorithm can really generalize across different disorders. And here, over the past few months, we have been able to design the adaptation algorithm, the robustness algorithm, and also theoretically establish the stability of this algorithm. And we are also able to do the first set of simulation where we just use neural networks, very general neural networks, to simulate the brain, and then we implement our controller. And here is a controlling example in simulation where over time, you can see that once you turn the stimulation on for the traces that we are using our controller, which are the cyan and black here, we can very accurately control at the target, while for different other controllers, they would miss the target. And the reason for that is because in this simulation, we deliberately add a lot of uncertainties and nonlinear dynamics. And we also show that compared with other controllers, our controller, which is here, the cyan ones, maintains a high percentage of stability when the amount of model uncertainty increases over time. And here, the steady state error of control, our controller is also small. So for the next steps, we are going to keep validating this using neuropsychiatric models, and we will also use the result to seek for external funding to develop precise and personalized DBS therapy for Parkinson's as the starting point, and addressing the several points that Dr. Berman has already raised, for example, the time-varying stress levels, as well as deal with the sleep patterns so we can save the DBS battery life. So yeah, the above is an introduction of our project. And again, I would like to thank CCS and COM for this funding opportunity. And I'm happy to take any questions.